everyone. We are Team PT4 and my name is Hajin. For our project in CSCI323 Model AI, we developed a facial expression recognition model. Our goal was to create a system that can automatically detect and classify human emotions based on facial features using deep learning. This project combines computer vision, neural networks, and emotional AI. In this project, we built a machine learning model that analyzes facial expressions and categorizes them into 7 emotions: angry, disgust, fear, sad, surprise, and neutral. We trained our model using FER 2013 dataset, which is standard benchmarking in the field of facial expression recognition. The overall goal was to replicate how humans intuitively read emotions, but with artificial intelligence. The dataset we used is FER 2013, available on Kaggle. It contains over 35,000 grayscale facial images, each 48 by 48 pixels in size. The dataset is already split into training and testing sets with a ratio of about 80 to 20. Each image is labeled with one of the 7 emotion classes. These pre-processed images help the model focus purely on learning emotional patterns without worrying about alignment or face size. To build and train our model, we used a wide range of Python libraries. TensorFlows and Keras were used for building the neural network. NumPy and Pandas helped with data handling and pre-processing. We visualized training results using Matplot library and Seaborn. OpenCV was used for webcam face detection, and Google Colab provided us with free cloud GPUs for training. We also applied data augmentation using Keras to improve generalization. Our model is convolutional neural network specifically designed for emotion recognition. It takes grayscale images as input, passes them through 3 convolutional blocks with conv2D, batch normalization, max pooling, and dropout to reduce overfitting. After flattening the output, we use a dense layer and finally a softmax output layer to predict one of the 7 emotion classes. The model was compiled with Adam Optimizer and categorical cross-entropy loss. This slide shows how we imported the essential libraries and loaded FER 2013 dataset. We also printed the emotion distribution to understand class imbalance. As seen in the chart, classes like happy, neutral are more represented, while disgust is underrepresented. This insight guided our use of class weighting during model training to handle the imbalance.
Hi all, myself Milin. I'll be taking over Hajin to talk you through the next few slides. Now let's look at data cleaning and pre-processing. So basically what we do here is clean the data set. We remove any rows where the pixel data is missing or broken. Each image is stored as a long string of 48 times 48 grayscale pixel values, and we convert that into a 4D NumPy array, which is the format of format what our CNN expects. Then we try to normalize the pixel values to a range of 0 to 1 by dividing them by 255. This just makes the training more stable and faster. And finally, we want hot encode the emotion labels into 7 categories, which basically just turns them into the format the model can understand for classification purposes. Moving on to data splitting and class weights. After cleaning, we split the dataset into training, validation, and test sets, roughly 64, 16, and 20 percentage respectively. We use something called stratified sampling to make sure the emotion labels are evenly spread across all the sets. But one issue with emotion datasets is that some emotions like happy are more common, while others like disgust barely show up. To fix that, we compute class weights so that rare emotions get more attention during training and the model doesn't get really biased. In the next slide we talk about data augmentation. Here we do some data augmentation in order to make the model more robust. Basically, we use Keras image data generator to apply real-time transformations, which include small rotations, zooms, shifts, and even horizontal flips. This helps the model learn better because it sees different variations of the same face. kind of like teaching it to recognize the same emotion from a slightly different angles or positions. It also helps reduce overfitting without needing more data. Next slide is about the model architecture. Here's the CNN architecture we are using. It's built in blocks, three convolutional blocks to be exact. The first one learns simple features like edges and textures. The second one picks up the more detailed stuff like eyes and mouths, nose, etc. And the third block digs deeper into more complex patterns. Each block follows the same pattern: convolutional 2D layers, batch norm, ReLU activations, max pooling to reduce size, and dropout to prevent overfitting. Then we flatten everything and pass it through a dense layer because before ending with softmax to predict one of the seven emotions. This is the full model summary. You can see the filter sizes increase from 32 to 64 to 128 across the three convolutional blocks, while the spatial dimensions get more smaller with the poly. Then we flatten the output, feed it into a dense layer with 256 neurons, apply some dropout, and finally output seven values, one for each emotion using softmax.
Hi, myself Cyril. I will be taking over milling. So in this slide, the model is compiled using the Adam optimizer with a learning rate of 0.001. So this helps in faster convergence. We use categorical entropy, cross entropy as the loss function, since this is a multi-class classification problem. The training runs for 30 epochs, as we said, and we'll be applying two callback parameters, which is early stopping and reduce learning rate on plateau. These help prevent overfitting and dynamically adjust learning rate if the model performance stalls. So in this slide, we can see that we can see all the 30 epochs, and we can see at epoch number 19, there's a learning rate adjustment happening. So for this slide, after training, we evaluate the model on the unseen test set to get a final measure of accuracy and loss. Here, the test accuracy is around 55%, and the loss is about 1.41. We also calculate per class accuracy, which shows how well the model performs on each emotion. For example, it does well on surprise and neutral, but it's struggling on fear and sad. So in this step, we visualize the training and validation accuracy and loss over epochs to monitor how well the model learns. If there's a big gap between the training and validation curves, it may signal overfitting. We also generate a confusion matrix using a Seaborn to analyze the model predictions across emotions. Initially, validation accuracy is near zero, so while training it's just about 20%, as expected from random guessing. From epoch 0 to 10, both accuracies steadily improve, indicating that the model is learning useful features. Between epochs 10 to 20, we observe some fluctuations around 45 to 50%, but the training and validation curves remain close, which suggests no major overfitting. Finally, both accuracies stabilize around 55 to 57%. So this would be a solid result given our datasets complexity and imbalance.
Hi everyone, my name is Faris and I'll be taking over Serial to continue on the evaluation aspect of our project. For this slide, from the diagram here, we can see the model's learning progress through its loss curves. Initially, both training and validation losses start high as expected. However, from epoch 0 to 10, there's a sharp decline indicating effective learning. Crucially, after epoch 10, the curves flatten and track each other closely. This close tracking with no significant divergence shows good generalization and that we've successfully avoided overfitting. The final stable loss around 1.5 is a solid result for this 7-class problem, especially considering the imbalanced FER 2013 dataset. Next, the confusion matrix gives us a detailed look at class-specific performance. The model shows strong performance for happy with over 1,300 correct predictions and surprise, which is also, I would say, highly accurate as well. Neutral also shows a high number of correct predictions as well, with 961 instances correctly identified. These emotions clearly have distinctive features our model detects really well. However, fear stands out as an area for improvement with only 167 correct predictions, often confused with surprise and neutral. Additionally, while neutral itself is often correctly identified, emotions like angry and sad shows lower accuracy, partly due to their frequent misclassification into the neutral category. These insights from the confusion matrix directly guide our next steps for improvement. For fear, we'll focus on enhancing feature extraction and possibly introducing more nuanced training data. For angry and sad, we'll explore why they're confused with neutral, perhaps by improving dataset quality or refining the model architecture for subtle cues. Finally, data balancing, particularly for emotion like disgust, which has fewer examples, will be key to learning more robust features across all classes. Moving towards real-time application, I'll briefly walk you through the initial Python code setup. First, we load essential libraries like OpenCV and TensorFlow. Then we load our trained CNN model, emotion model 30epochs.h5. Finally, we define clear emotion labels. This dictionary maps the model's numerical output to human readable expressions like angry or happy, which is crucial for easy interpretation of the results and for general usage as well. Next, to capture live input, particularly in an environment like Google Colab, we use a snippet of JavaScript. This function allows us to access the webcam, prompt the user to capture an image, and then save the image locally. This captured image is then ready to be processed by our model for real-time facial expression recognition. Now I'd like to pass things over to Wen Liang, who will be continuing on this aspect of our project. Thank you.
Hi guys, my name is Wen Liang and I'll be taking over the presentation, further elaborating on the codes used in our model. After the model is trained, we will then put it to use using real-life examples, and this is actually where the second portion of our program actually comes into play. So referencing from the screenshot shown in the slides, this is the function that we'll use to actually capture and process the image captured by our webcam as explained earlier by my group member. So this function will actually load and convert the captured image to grayscale, and it will then detect the face. It will normalize and resize the image to 48 by 48 as required by the model. Once the normalization and resizing is complete, it will then predict the emotions using the trained CNN model, whereby it will then display the bounding boxes around the face and then show the results of the top two emotions with confidence percentage. An example of the output will be shown later on in the slides. So we also have another function called run emotion detection, which will simply just act like a loop to capture multiple images at one run. The user will be prompted to capture each frame manually, and by default, we just kept the repetition to 5 to capture 5 different frames to see the results of the output. So regarding the output, these are some sample of the output made by the model in classifying the different facial expressions. As you can see over here, there are different faces shown, and the results predicted by the model are also different. So that in each of the faces, there are actually two different emotions being predicted, accompanied by their confidence percentage. And if you see over here, the bottom left images, it displays two emotions, angry and disgust, with disgust having a percentage score of 74.4, which shows that the model predicted this facial expression to be leaning more towards disgust rather than angry. So challenges and improvements. So even though the model earlier on was able to predict the images correctly, but there are also times whereby the model predicted the emotions incorrectly. So this could be caused by multiple factors in which are the challenges that we face lah. So one of the challenges that we faced was actually due to the nature of the data set that was being used. there was a huge class imbalance between some of the emotions. The discussed class actually totaling up to only 547, which only makes up about 1.5% of the entire data sets. So with such small sample of data set to work with, the accuracy would definitely be lesser compared to the other classes. Emotions such as sad and fear have similar visual cues, which also may lead to the model being confused between the two classes and therefore not being trained well enough, and hence resulting in lower accuracy as well. And the images used in this project are not in a very good resolution as well. So this will affect the training process of the model. So some improvements that we can make to counter these challenges is actually to use images of higher resolution and also implementing data augmentation that specifically targets minority classes to cater for their lack of sample. Also, programming the model to focus more on key expression areas such as eyes, brows, and mouth could improve the training process of the model as well. All in all, in this project, our team have developed a real-time facial expression recognition system that can predict facial expressions using webcam. Though the results and accuracy might not be the best, our group has have learned much in the process. Some key takeaways from this project includes the importance of data augmentation and how severe a class imbalance can actually affect the whole entire training and the model. And also, we through this project we learn how to implement a more effective CNN design. And yeah, that's all. With that, I have come to the end of my presentation.